For those of you who are not familiar with drug delivery system, a drug delivery system is an engineered system for targeted delivery and/or controlled release of therapeutic agents. For example, if a person has an injury or symptoms that needs to be controlled, the use of a drug is typically employed just to increase the health of that patient. A drug delivery system is able to release a drug on a desired location and on a controlled fashion. There are three typical areas based on the drug concentration in the body. There is the toxic, the therapeutic, and the subtherapeutic range. The therapeutic range is the ideal concentration of a drug to treat any desired condition. Above, we have the toxic range, which it can cause adverse reactions and are obviously not desired. Finally, the subtherapeutic range, which the drug concentration is below the ones that are needed to treat any condition. The ideal concentration profile is the one that reaches the therapeutic range and then remains there over time. Here we have a typical route for drug delivery system to administrate a desired active ingredient. The common ones are the oral, parenteral, ocular, and transdermal. Each of them offer advantages and disadvantages according to the desired application. One of the main disadvantages of typical drug release vehicles is that not all the drug is effectively used. Typically, around 20% of the drug usually goes to waste, sadly. In this presentation, we will focus on the electrospinning and electrospraying technique and how they are used to create drug delivery vehicles, specifically with the Fluidnatek technology. But why using electrospinning or electrospraying? One of the main keys is that a wide variety of materials can be used. If you're making fibers, they provide high surface to ratio, which is key for filtration processes and energy storage application. They can also mimic the extracellular matrix in an easy fiber formation process. Fibers and particle diameter can easily be controlled through processing parameters. The typical range is 20 nanometers to 10 micrometers, but higher than that can be achieved with proper solution development. With electrospinning and electrospraying, we could easily encapsulate any material in the fiber or particle in what is known as a core shell rearrangement. We can easily also obtain fiber orientation, either random or aligned, by using the right accessories. I'll come back to this later on in the presentation so you can see some of the examples. Both of these techniques are able to process fibers and particles at room temperature, and then this is really suitable for the use of thermolabile materials. When I say thermolabile, it's materials that are sensitive to temperature. So this is really important, especially when polymer blended solutions are needed. Typical fiber formation like hot melt extrusion operate at high temperatures. Therefore, if you're using a polymer blend, unwanted copolymerization cannot be controlled. Therefore, instead of having two materials, you're going to combine them and have a non-desired material. And then with solution electrospinning, this all can be avoided. The diagram in the left shows the electrospinning setup on its most basic form. We have a polymer solution that is pumped into a capillary needle using a syringe pump or other pumping method. A high voltage is applied into the needle. As the voltage increases, electrostatic forces act in the solution. Due to charge accumulation in the tip of the needle, the drop changes into what is known as the Taylor cone, which is also shown here in this left diagram. At this point, a liquid jet is ejected, and due to whipping and bending instabilities, the solvent is evaporated during the process. Eventually, dry fibers are collected into a collector. So this process can be seen in the image in the middle. This is actually taken using our Fluidnatek equipment. So according to the polymer solution and its properties, we can obtain either electrospun fibers or electrospray particles. One of the important aspects about this technology is that it can produce a dry product in a single step. Because the electrospinning and electrospraying techniques can operate at room temperature, drugs that are sensitive to temperature can easily be processed without affecting their activity. So for example, we can easily process protein, peptides, and amino acids without changing its native structure. There are various ways to load a drug into electrospun fibers or particles. These include blend electrospinning, in which a drug and polymer solution are completely blended in the solution to then obtain uniform distribution of the drug around the fiber or the particle. We also have core shell encapsulation. In this case, the drug is inside the fiber or the particle, and the drug can be protected from the harsh in vivo environment and avoid hydrolysis over time, if that will be the application. And then finally, we also have physical absorption and chemical immobilization. In these two cases, the drug is loaded after the sample is created. Based on this, an electrospun mat or electrospray particles can achieve specific drug delivery rates. Another advantage of using electrospinning or electrospraying techniques for drug delivery applications is, is that we can use any type of material. So for example, natural polymers like chitosan, gelatin, and cellulose. Synthetic polymers like polyethylene terephthalate or polycaprolactam can also be used. Depending on the polymer structure and chemical properties, targeted degradation to release a drug can be achieved. If you want the drug to be diffused, or if you want the drug to stay inside the fibers or the particles and then burst, depending on the polymer, we can also work around that. So for example, we have surface degradation in which the polymer slowly degrades in the surface and decreases its diameter over time. And then we also have the bulk degradation in which the whole polymer degrades slowly over time, retaining its main structure. Based on all these properties and depending on the location for drug delivery system, targeted mechanical properties can be achieved based on degradation properties. Some of the applications that are around drug delivery include tissue engineering, wound healing, oral capsules, burst delivery, animal population, film strips, for local delivery, for example, implants, I mean, you name it, there's so many of them. So during this webinar, I'll be discussing the delivery system shown on these two tables. So for example, we have a vehicle in single phase, which we can have particles, just one second, we can have particles in single phase and also fibers in single phase. We can also have core shell encapsulation in which we can add a drug inside the fiber. And then it can be one drug, two drugs, three drugs. So we can control all that. We also have tubular capsules using electrospinning. So these capsules, you can add more drug as opposed to typical electrospinning setups. I'll come back to this later on. And then if we sinter the sample and we properly create a sample, we can have even films with controlled porosity in the nanoscale to improve drug delivery. So to introduce you everybody to our electrospinning machine, we have 4 different units that are made by BioNisha. Us, NanoScience Instrument, are the exclusive distributor of the Fluidnatek equipment in the United States. The LE100, so we have 4 ones, right? The LE10, which is a benchtop unit, which is mainly used for basic research and proof of concept. We also have the LE50, another benchtop unit for more advanced research by offering an airtight and thermally insulated chamber. So the LE50, LE100, and the LE500, they all can be implemented with an environmental control unit, which I'll be talking more in a few slides. So when I'm saying environmental control unit is that we can control temperature and relative humidity during the spinning process. So we also have the LE100, which is a larger unit able to give you unique features for advanced research and development. For example, the needle tip or the emitter or the nozzle, depending on how you would like to call it, we can move that in X, Y, and Z axis all at the same time if needed. We also have the LE500, which is aimed for pilot scale and pre-industrial stage. It has the ability of collecting fibers in a roll-to-roll collector, and actually we can go all the way up to 112 emitters if needed. All units allow the tight control of fiber dimensions and stability of fiber and particle production over time. They are also scalable, so a solution recipe that we start using in the LE10 can easily be transferred all the way to the LE500 with ease. Our units are actually GMP certifiable and scalable, allowing the technique to even be scaled to a production plan. As a matter of fact, BioNisha, the manufacturer of these units, they also have the first and only GMP certified plant for the production of fibers and particles for pharmaceutical applications. The Fluidnatek can be implemented with over 26 accessories that can be upgraded at any time, which is a really nice, unique feature. So here I'll be showcasing some of the selected capabilities for drug delivery. But before I start, everybody that is working with home-built units, they know that it's not safe to say it that way. This brings safety concerns, especially because we're operating at high voltage. You could easily be using organic solvents that are flammable, toxic, and can cause health issues if proper ventilation is not provided. If they are used in a university, this could bring liability concerns due to exposing the students and researchers to all these non-safe aspects. The image in the middle shows a typical home-built unit, so the end user is not maximizing their fume hood space as it needs to be operated inside the fume hood to avoid solvent exposure. All components are also separated from each other, meaning that you need to operate them separately, increasing your chances to get exposed not only to high voltages but also to organic fumes. All this can be obtained by using safety-oriented, properly professional equipment like ours, the Fluidnatek. One of the main aspects for our Fluidnatek equipment is that all of them are safety-oriented. The parameters are controlled from a touchscreen panel, preventing the user to be exposed to any of those adverse components. For example, the image is showing a close-up of the tab that controls the temperature and relative humidity and also the airflow. So if I go just 1 second, so we have that option for controlling the AC, so temperature, relative humidity, and also the airflow. But here in the side, we have the option to control the voltage, control the flow rate. For this specific unit, we can control X, Y, and Z axis. And then we also have the option of controlling the RPMs because a rotating collector is implemented in this specific machine. So all units have a safety shut-off button in case the process needs to be completely shut off for any reasons. And then I also want to say that the chamber is made of stainless steel, aluminum, and glass frames and enclosures. Virtually any solvent can be used. Meanwhile, if a specific solvent that is not compatible with any of these materials is needed, we can also engineer the unit to your needs. Another feature with the Fluidnatek is that we can create fibers and particles in single-phase, core shell arrangement, and even multi-axial. For single-phase, blended or non-blended materials can be electrospun and electrosprayed. Additives can also be incorporated according to the application needs. For example, growth factors can be blended with the polymer solution before electrospinning. This will further improve biocompatibility with the in vivo environment. If that growth factor needs to be added after the sample is created, we can also go around that. Fibers can have different physical properties by using different solvents. For example, electrospinning polycaprolactone with either acetone or dichloromethane. In this image you're seeing, so let me just get this. So in the image A, we have polycaprolactone with acetone. In the image B, polycaprolactone spun with DCM or dichloromethane. So by same polymer, same concentration, depending on the solvent that you're using, you can give different features to that polymer. So smaller fiber diameter when acetone is used as opposed to larger fiber diameter when DCM is used. And then this is mainly because DCM evaporates faster as opposed to acetone. So we can also go around core shell and multi-axial structures with the Fluidnatek. For core shell fibers, this means that we're processing two solutions at the same time. So one will be in the core, which is here depicted by the yellow, and one in the shell, which is the clear solution. This is easily done by having a needle inside a second smaller needle. At the end, we will have really beautiful coaxial structure that can be encapsulating a drug or any other additive that is needed. In order to avoid non-reliable results, controlling temperature and relative humidity is really crucial. But why is controlling these two parameters really crucial? As you may know, temperature and relative humidity have strong influence on how the solvent evaporates during the electrospinning or electrospraying process. These two parameters strongly influence according to the location and season of the year. If your building facilities are not too well controlled, you can easily see dry conditions during the winter, high humidities after it has rained, or even fluctuations during one single day. Due to this, batch-to-batch reproducible results may be hindered. And then just for an example, I did my PhD in Ohio State, and in Ohio, the relative humidity changed all like crazy. So it's really crucial to control all these in order to have batch-to-batch reproducible results. If we control these two parameters, you will not only get reproducible results all year long. If a GMP certification is needed, this will maximize batch-to-batch production and also reproducibility. The image in the right is a clear representation when the climate conditions are not controlled. The solvent is just evaporating too fast, polymer is partially solidified, and the emitter in the emitter, and then secondary jetting may be happening. So if you have the primary jet and also secondary jet, that means that the fiber distribution is not going to be consistent. You're going to have different fiber diameters all around your sample. So in this case, if we control the electrospinning conditions, but then also improve the relative humidity, this specific solution will be able to create a better electrospinning process. So what does NanoScience Instrument, along with BioNisha and the Fluidnatek, offers? We offer you 4 years of climate control expertise. We tightly control temperature, relative humidity, and airflow with ease. But then why also airflow? Solvents that are evaporating during the electrospinning or electrospraying process will accumulate if not properly removed from the chamber inside our units. Therefore, if they are not properly removed, you will not obtain batch-to-batch reproducibility, as this will also affect the electrospinning and the electrospraying conditions. So the first image is showing our LE100 unit with the climate conditioning control unit and how they are attached between each other. So all the air is conditioned in the environmental control unit. So once the air is conditioned in this unit, it goes directly into the main LE100. That means that the conditions inside the chamber are going to be consistently the same as you input in the machine. So if you want to have, for example, let's say, so one of the things that we can control the temperature from 18 degrees all the way to 45 degrees. In terms of relative humidity, we can go from 10% all the way to 80%. So just as an example, if we're operating at 25 degrees, that means that the relative humidity that can be operated inside the chamber can be from 30% all the way to 75%. So another example, let's say that we're operating at 45 degrees, we can control the relative humidity from 10 degrees all the way to around 25%. Yeah, so this is really crucial for controlling and then have batch-to-batch reproducibility. But then why will this be the case? When you're properly controlling both of them, you're going to be able to have more consistent results. So, and then you're going to be able to avoid any non-desired imperfections. So for example, we have here dust in these two cases. We also have fiber bundle, fiber bonding, and more fiber bundles, and also beading. So if you have a drug that is encapsulated in the fiber, imagine a big amount of drug that is going to be encapsulated in this bead. That means that whenever you're doing any drug delivery research or drug delivery application by itself, the drug is just not going to deliver consistently. But meanwhile, if we control all the temperature, relative humidity, and every single parameter during the electrospinning process, we're going to have really beautiful, perfect nanofibers. And as a matter of fact, this specific sample, the standard deviation is less than 50 nanometers. So imagine that. That's really crucial, especially for drug delivery applications. So with the Fluidnatek equipment and when controlling temperature and relative humidity, you will be able to obtain consistent fiber and particle diameter. This not only will create homogeneous fibers and batch-to-batch reproducible samples, but when a drug is loaded into the fiber or particle, proper release will be achieved. Drug delivery on fibers and particles will depend on drug concentration, delivery structure, and structural parameters. So for example, in this image, for drug concentration, obviously, if you have more drug loaded in the fiber as opposed to one that is not too much loaded, the one that has more loading of drug is going to deliver the drug faster. In terms of delivery structure, if you're using a single phase fiber versus core shell fiber, if all the drug is encapsulated in the core, the single phase, which is this case, the drug is going to deliver faster as opposed to the core shell rearrangement. And that is because the drug needs to go and diffuse all around through that shell phase. And then we also have structural parameters. We can control drug delivery based on how the fibers are, like if the fiber diameter is smaller versus the fiber diameter is bigger. So if the fiber diameter is smaller, the drug delivery is going to be more fast as opposed to the one with larger fiber diameter. An example on a drug delivery system is the Riveling patch, which is made in BioInitia's GMP plant using our Fluidnatek technology. To improve drug delivery, these patches deliver the drug in only one direction, which is the affected area. This is made possible by the use of a two-layer vehicle. The first layer is the bioadhesive layer made of a hydrophilic electrospun fibers containing the drug. So this is the slide. And then the second layer is the impermeable hydrophobic layer. Thanks to the hydrophobicity of this layer, the drug can only be delivered in only one direction. The image on the right shows the actual electrospun fibers, the cross-section of the patch showing the dense hydrophilic layer, the actual sample, and the patch in action of the affected mucosal area. So once again, we have here a protective layer which is completely hydrophobic and then is completely dense. If we look here in the SEM image, you can see that dense layer that actually helps the drug to be delivered in only one direction. Again, here is that hydrophobic layer, and because of that, the drug is only delivered in this direction. And then the electrospun fibers is the one that has that drug encapsulated in the fiber, and then it's a hydrophilic material. All right. And then in terms of collecting fibers and particles, by these techniques, we require a collector. All Fluidnatek units offer multiple collectors according to your research needs. We have flat plate collectors for either random structure or particles, or we can also create 3D structures, kind of like similar to 3D printing. Rotating drums for aligned fibers when high RPMs are used. It can also be used for random fibers when low RPMs are used. A rotating mandrel can also be implemented for different applications like tissue engineering. So for example, researchers are using these mandrels to create beautiful artificial blood vessels, shape craft. This can be later implanted on a patient as needed. So we also have a roll-to-roll collector, and then this is mainly for pilot scale industrial unit, the LE500. This allows the user to continuously collect either fibers or particles. By combining this with 96 simultaneous emitter in this case, or in how this image shows, the throughput will be maximized and the spinning time will be reduced. Another of our collectors available in all units is the rotating disc. This collector is mainly used to collect aligned fibers due to the small exposed area. So the area in this disc is really small, and then because of that, we can collect aligned fibers on it. Anyone that uses a home-built unit knows that creating homogeneous thickness in the sample is really challenging. With the Fluidnatek, this is an easy process that is done by having a meter movement in either 1, 2, or 3 dimensions. The video in the left is showing our LE500 with a rotating drum and the emitter being displaced in one dimension. So it's displacing in the y-axis. So not only we're improving sample thickness because the sample is completely just collecting all around that whole area. Depending on the RPMs that we use in this drum, we can create either aligned fibers or random fibers. For aligned fibers, we use high rotating speeds, and for random fibers, we use low rotating speeds. Meanwhile, similar to 3D printing, our electrospinning units can create this beautiful 3D patterning like scaffold. So you can see that from looking far away, it kind of looks like only one big fiber, but then if you look closely, you can see this really interesting pattern that is really small fibers and the actual main whole sample. And then here we're looking at the microstructure of aligned and random fibers also. One of the interesting things that I have been making with these units, so we have first what is known as super aligned fibers. So these fibers are typically stronger than randomly oriented fibers, and they can be used for neurological applications. Interestingly enough, with this machine, we can create metamaterials. So metamaterials are materials that have properties that are not typically found in nature. So for example, in this case, you can see once the fiber is completely in contact with the solid, you can say that it becomes invisible. So So this is really interesting because we can use this for drug delivery applications. So for example, if you want to hide a patch that is delivering over time, that way no other people can see that you actually have a patch in your hand, for example. Yeah, so these are really interesting samples that you can create with our electrospinning units. Oops, go back. So typical units operate with 1 emitter needle or nozzle, again, depending on how you like to call it. Depending on the Fluidnatek unit of interest, we can operate from 1, 5, 10, 20, 24, and all the way up to 112 emitters at the same time. This allows you to increase the throughput by implementing what we call multi-emitter spinning heads. Not only we can do single phase, we can also operate in core-shell mode with simultaneous emitters. The video in the left is showing how we're using 40 emitters with the LE100 to go through either spinning or spraying processes. And the images in the right show you some of our multi-emitter spinning heads. If we want to use 96 emitters, or if we want to go all the way to 112 emitters to be used simultaneously to increase sample throughput. All right, so another possible drug delivery that we can create with the Fluidnatek electrospinning technology is Electrospun capsules. This is actually a really new and interesting way of doing drug delivery. Typical Electrospun samples are limited in terms of drug loading. With an Electrospun capsule, this disadvantage is completely removed because we have the capacity to increase drug loading. This means that long-term release for up to a few years can actually be achieved. So these images show the Electrospun capsule in the left, which is made in a rotating mandrel. Upon close inspection, we can see that the Electrospun fibers on the surface of that Electrospun capsule. Once this sample is completely removed from the mandrel, we're going to obtain a hollow capsule. And then on that hollow capsule, let me just get these. We can target it to have different properties. So for example, number 1, it will be the drug that is encapsulated inside that hollow tubular scaffold. The second one will be the capsule wall. This will be your material, and then it can be, we can control the drug diffusion, number 3, based on the drug and also the capsule wall that we're using. One of the interesting things is that depending on the polymer that you're using, if you have a low melting point polymer, you can post-treat that sample after you make it to decrease the porosity. So let me get to the next slide so you can see that. So for example, here I present how the Electrospun capsules are heat treated. So in this case, we have polycaprolactone. So polycaprolactone has a melting point of 60 degrees. So because we know that if we have a really large porosity and then we have a liquid inside, that drug is going to tend to diffuse really fast and then it's just going to burst. So that may not be the ideal case or the desired final needs or applications or expectations, but because the melting point of this polymer is really low, it's around 60, we can just sinter that sample at 56, 57, 58, and 59, and then you can see that the morphology of that surface is going to change, so the porosity is also going to change. So once we're really close to the melting point, 58 and 59, the whole sample completely densifies. And then at the end, for example, the 59 Celsius capsule, so we treated this capsule at 59 degrees for 3 hours, it becomes completely a solid, like a film-like. So in here, we added 40 microliters of a model drug, and the concentration is 20 milligrams by mil. And then you can see that we have even more capacity of drug loading. So depending on the dimensions of your capsule, you can just add either more drug or less drug as needed. And then depending on that post-treatment and the porosity, you can change the release rate. So for example, at 56 and 57, that release is really fast, and then it's because we have a lot of porosity in there. Meanwhile, if we decrease the porosity up to when it's almost a completely film, the drug is released by diffusion. So it's a more controlled release. So let's say that you want to have a drug that is slowly delivered over time for longer times. This will be the ideal way to go using the electrospinning technology. And then why using the Fluidnatek? Since we can actually have a more controlled process, that sample uniformity is going to be more controlled also. But then the previous slide was mainly for using drugs in terms of liquid. Meanwhile, since we have a dense capsule now, we can even use solid drugs. So for example, in this case, we have around 50 milligrams of a drug, but then meanwhile, we can actually go more than 1 gram. It will be possible depending on the fiber the actual diameter of the capsule, and then the length of that capsule. So again, any liquid and solid can be used. Depending on the polymer that you're using, you can control the strength also of that material. And then in terms of the carrier, you can add different carriers. So for example, let's say that a drug that you're using can go through hydrolysis. So instead of using water as a carrier, you can use an oil, for example. And by using an oil, you can actually control how that drug is delivered. So for example, in this slide, we're using the same system that we're showing here. This capsule has the model drug inside, which in this case is rose bengal, a fluorescent dye. The oil can be completely hydrophobic oil, so it's not going to allow the water to go inside that capsule. In that case, the drug, you can see that it's not delivered over a period of 8 days. Meanwhile, if we have a hydrophilic oil inside, we can actually control that drug delivery. And then in this case, you can see that there are actually 2 different rates. And then that's mainly based on the that this capsule is actually a blend of polycaprolactone and polyethylene terephthalate. So depending on the concentration of those polymers, you can also control that drug delivery over time. For instance, we can have a higher release rate when more concentration of PCl is in the capsule, as opposed to when we lower that concentration to 75% PCl, the drug release is more hindered. And then this is not always going to be the case. This is also going to depend on the drug that you're using and how that drug interacts with the 2 polymers and how it diffuses over time. But then, meanwhile, if that drug is just delivered too slow, we can actually use organic salts. If we use organic salts or inorganic salts in solution, we electrospin those and then we completely densify them. What we're gonna have is just a completely dense film of the polymer that you are looking for, but then we're also gonna have some agglomeration of the salts that you're using. But then if we expose this polymer, the polymer film into water, we can just leach out all that salt to completely create nanoscale porosity all around. But if this is just like too much large for your drug delivery application, we can just decrease the ratio of that salt to create more homogeneous porosity all around your sample. So in this instance, we only have 1% of an organic salt. And then after we remove it completely, you create these beautiful, nice distributed pores all around the sample. And this is not only in the surface, this goes all around through the cross-section of the sample. And then some people ask me, like, well, you're using electrospinning, but then you're just completely destroying that fiber structure. Well, that's true, but that doesn't mean that you cannot have that fiber structure in place. Electrospinning is such a beautiful technique that it allows the use of so many materials. So for example, we can have this dense layer as the ones that we have been describing before. But if we use the proper polymer solution, for example, PCl with gelatin, the blend of a natural and a synthetic polymer, we can create Electrospun PCl gelatin fibers. And then since they are resistant to heat, that means that we can sinter this sample, and the fibers and the dense film, they're going to completely fuse together, to say it that way. And then at that point, you're going to have your electrospinning Electrospun fibers along with the dense polymer. And this is going to avoid the lamination by just combining those through heat treatment. And after that capsule has been, the dense layer has been incorporated into the fibers, you can then add the drug. So there's no need to worry about exposing that drug into any of the thermal instabilities during that process. And then in terms of drug delivery, another thing that is really crucial, it will be the thickness. So if you have a Electrospun capsule or Electrospun sample that is around 100 to 140 micrometers in thickness, that drug is going to be delivered really fast because that thickness is just small. Meanwhile, if you're controlling the thickness and adding more and more material, creating an example up to like really close to 800 micrometers in thickness, that drug is not going to deliver as fast and it's going to be more controlled. And then this is mainly due because that drug needs to go through a tortuous path all the way to the outside layer. So we can actually control sample thickness. Meanwhile, if you're using like a regular home-built unit, the thickness distribution may not be well distributed. That's why the Fluidnatek is really important to be used to create more consistent batch reproducibility. One, if you're controlling temperature and relative humidity, fiber distribution is going to be more controlled. Second one, if you're using emitter movement, you're going to have a more distributed sample in terms of thickness. And then the third one will be this one that is coming. We can actually measure the thickness in real time if the right accessory is employed. So this is really important because anyone that works with electrospinning knows that sample thickness measurement is not easily done. What people usually do is that they measure the samples using calipers. So if you're just applying too much pressure, you're going to get a false thickness. And then that's why we offer this real-time thickness measurement. So we work directly with our customers to engineer this accessory to your needs. It will be always a high precision accuracy package that can measure over 10 millimeters in range. We also offer a traffic light signal feature. And then this is mainly to know the status of your desired thickness over time. So for example, if you want a 100 micrometer sample, the light will be changing from red to green as it reaches that desired thickness. A feedback loop can be implemented with the emitter motion to properly reach that thickness. And then once it reaches that, it's just completely going to stop. And then you're always going to have consistency in terms of like thickness. A beautiful advantage of the Fluidnatek is that for the LE50, the LE100, and the LE500, we can implement the unit with two independent high voltage sources. This means that two different solutions can be processed simultaneously. So for example, the video in the right is showing how two non-compatible solutions, they cannot be blended by themselves. We process them separately. So if you have a drug that is not compatible with the polymer solution, for example, you can just process them both separately. So the Electrospun fibers with one high voltage and then the drug through the other voltage. And then this means that we can create either two different fibers or two different particles simultaneously, fibers and particles at the same time, or fibers and cells. And when I say cells, it's because the electrospinning and electrospraying technique usually doesn't implement really high currents. So the cells is going to be able to survive that whole process. And then again, just so you know, we have over 26 plus accessories that can be implemented at any time. If you're trying to acquire one of these units, you don't need to get all the accessories right away. We can work directly with you, go directly to your site and then install that. So we offer GMP certifiable units. We can actually just make sure that they're completely certifiable to your needs. We also offer a UV lamp. So if you want to sterilize the chamber before or after processing, we can work with that. We also offer HEPA and ULPA filters. So for the air that is going inside the chamber, just to make sure that the whole sample that you're making is completely clean. And if needed, we can also apply one for the air that is going outside of the chamber. If you want to see the Taylor cone during the spinning process, just to make sure that the whole process is completely stable, we also offer that Taylor cone visualization system, so you can see it above the touchscreen panel. If you're working with a solution that needs really, it doesn't dissolve really well at room temperature, we can also implement a syringe heater. That means that we can apply heat in solution from all the way up to 120 degrees Celsius. We can also operate the unit in terms of time and different processing parameters. So let's say that you're working the first 5 minutes, you want X, Y, and Z conditions, and then from 10 minutes to 1 hour, you want other different conditions. So we can actually implement what is known as a programmable sequential multi-step recipe option. So it's going to control all the parameters by time. And we can also implement that recipe in any of these systems. And then one of the nice things about this unit is that they can be customized to your needs. For example, here in this image, I'm showing the Bio, what is known as the Bio LE100. This is completely made in stainless steel. It doesn't have any gaps or crevices. So it's completely cleanable, really easy to use, and ideally for pharmaceutical applications or drug delivery applications. And then lastly, I would like to remember everyone our analytical services. We offer process development and optimization of your current electrospinning solution. We also offer characterization techniques like wettability and contact angle for when the hydrophilicity of your sample is needed. We also offer microstructure analysis, just in case you want to see the microstructure of your sample. It doesn't need to be Electrospun. It can be any type of material that you want to see the microstructure. And if you would like to have a demo of this unit, feel free to let us know. Here in Phoenix, we have the LE100 with the environmental control unit. You will be more than welcome to come and see the unit by yourself, and you'll see why it's so awesome.